Ta-da!
Okay, well, hello and welcome to the official grand opening event of the Printed Circuit Engineering Association. My name is Mike Buteau. I'm the editor-in-chief of Printed Circuit Design and Fabrication and Circuits Assembly and a board member of the PCEA. We are really glad that you can join us today. Our guest presenter, Rick Hartley, will be on in just a moment. But first, I'd like to ask everyone who is joining us live to complete the short survey so that Rick can have a better sense of who's in the audience today. And while you're doing that, I'll also take a moment to explain the question and answer procedure. We will be taking questions throughout the entire presentation, which will last about an hour. We will wait until the end to address them, so we don't interrupt the flow while Rick is talking. When Rick finishes, we'll stay on for a few minutes to address a few of the questions in the queue. If we don't get to yours, please don't worry. We will send out a post-event survey in the next 24 hours, and you can use that survey as an opportunity to re-ask your question. Be sure to include your email, and we will attempt to respond and perhaps post a question in response online. Okay, I see the poll is up. It will only take you a moment or two to finish that, so please go ahead and do it. And I'd also like to introduce our panelists. They are here to address any questions you may have on the PCEA. We have with us Michael Creedon, who is the Vice President of the PCEA, Scott McCurdy, who is a PCEA board member and President of the Orange County and LA chapter, Gary Ferrari, another PCEA board member and co-author of the CID and CID Plus exams. And finally, I would like to introduce Steph Chavez, who is the president of the PCEA. Steph, the virtual microphone is now yours.
Thanks, Mike. Hello, as Mike said, I'm Stephen Chavez, chairman of PCEA. Welcome to the Printed Circuit Engineering Association's virtual grand opening. Let me first start off by thanking UP Media Group for hosting this virtual event, our featured speaker, Rick Hartley, and each of you for joining us today. This will be the first of many events to come from PCEA as we have hit the ground running. I also want to thank UP Media Group for being one of our initial sponsors of our association and for continuing to allow us to produce the column, The Digital Route, on their website. To date, the Digital Route has been a great success and very well received within the industry. I'm very excited to speak to you today about PCEA, explaining who we are and what we're all about. A lot of hard work and lots of long hours of effort by some very passionate individuals who make up a leadership team of PCEA has gone into getting us to this point where we are today. We have solidified the foundation and the incorporation of PCEA, as well as released our official website, pce-a.org, as of June 1st. I want to personally say thank you and an outstanding job done to the entire PCEA leadership team for all of our exceptional efforts for bringing PCEA from concept to reality. Let's start off by letting you all know who PCEA is. PCEA is a nonprofit organization, a 501c6. We're an international network of engineers, designers, fabricators, assemblers, and anyone related to the printed circuit engineering development. Our core is our mission statement to collaborate, inspire, educate by promoting printed circuit engineering as a profession. Our goal is to encourage, facilitate, and promote the exchange of information and the integration of new design concepts through communications, seminars, webinars, workshops, and professional development through a network of local and regional PCEA affiliated chapters. To date, we have over 1,000 plus members worldwide and continue to grow daily. We have 8 PCEA affiliated chapters throughout US and Mexico, with 5 additional chapters in the forming stages as PCEA continues to grow. These are exciting times for PCEA as we continue to grow and gain positive momentum within the industry. The PCEA foundation structure includes an executive board, education, and other committees. Our chapters are organized as self-governing bodies PCEA is directed by the Executive Board as selected from the active members of PCEA. Now let's talk about the ongoing objectives. PCEA is about meeting today's industry challenges from concept, engineering development, and standard implementation, and manufacturing, including fabrication, assembly, test, compliance, and field service. This knowledge includes details concerning printed circuit board materials, components, manufacturing process, allowance, and limitations. The final product should have high producibility, reliability, and yield. This should all be confirmed by quality assurance and compliance. The Printed Circuit Engineering Association is structured for these challenges. Our objectives are to, 1, stimulate communication among and between printed circuit board designers and other related engineering disciplines. 2, disseminate information regarding current activities and new developments in design technologies via newsletters. 3, maintain the communications link between standard bodies related to printed circuit engineering and manufacturing. Coordination includes, but is not limited to, the activities of government, industry, trade, and associations, and special interest groups. 4, coordinate the compilation of design standardization issues in printed circuit fabrication, assembly, with related design technologies. 5, encourage and coordinate the compilation of design information, including equipment capability, tools and technologies, and related information. 6, promote the necessity of early collaboration between engineering, fabrication, assembly, test, and field service. And 7, assist in the participation of suppliers and OEMs in chapter programs. I want to end by thanking all of our initial sponsors, iConnect 007, UP Media Group, Altium, and PCB Libraries for their initial support of PCEA. We have several other industry sponsors stepping up to the support of PCEA as well. We encourage you to join our family of sponsors. Lastly, I want to thank all of you for attending our virtual grand opening today. As I stated, this is the first of many such events to come from PCEA. So stay tuned, and if you haven't joined PCEA yet, I highly encourage you to do so by visiting our website, pce-a.org. We'd love to have you join and be a part of the PCEA Collective. Now, let's move on to the feature presentation by a near and dear friend of mine who needs no colorful summary or any fancy words of introduction. The one and only Rick Hartley presenting another one of his outstanding presentations. Rick, take it away.
Thank you, everybody, for attending. This presentation, as you know, is a short one. It's going to be, we're probably going to talk for 45 minutes or so, and then try to answer as many questions as we can. And as Mike said, we'll extend questions afterwards for those of you that don't get your questions answered. Just type your question in, and they'll be collected during the presentation. If you have a question pertaining to a particular slide, be sure and note the number on the slide. There are numbers at the bottom of all the slides after this one. And again, we're going to just talk about some tips on power distribution. I'm doing a 3.5-hour version of this class at PCB West. PCB West will be virtual this year, online, of course. And anybody that's planning on attending, if you like what you hear today and want to hear more, there is, again, a 3.5-hour version of this that will have a lot more information in it at that presentation. So all of that said, let's just get rolling. This first slide really has nothing to do with power distribution, but it's imperative that I make the point because it's critical to understand. The energy in a circuit is not in the voltage and current. I was taught in college that voltage and current are where it's at, and I've learned since that that's not the case. Energy in a circuit is in the electric and the magnetic fields. And more than that, more importantly even than that, the energy is not in the trace and plane in a transmission line. In other words, the energy is not in the copper. The energy is in the space between the copper features. So if you route a trace above a plane, the energy will travel in that dielectric space between the trace and the plane, the plastic of the circuit board. When I first realized the significance of this, it blew me away. And I'm going to tell you in a minute why this is significant to power delivery. As the energy moves through that space, it travels from the driver to the receiver, and in the process of doing so, it generates electron movement, what we called current flow, in the trace in one direction and in the plane in the other direction simultaneously. I can't tell you how many engineers I've met who've said to me, yeah, when you launch a signal, it travels down the trace to the driver and then it returns back to the source through the plane. Incorrect. The energy travels through the copper or through the plastic and it generates electron movement simultaneously in both directions. That's how it actually works. Why is this important for power delivery? Because power delivery is in the space between the planes. Think about that a second. I asked an engineer recently, where's the power in your circuit board? And he said, oh, it's on layer 2. And I said, incorrect. Where's the ground plane? Oh, he said, that's on layer 5. And I said, oh, then power is being delivered from the dielectric space between layer 2 and 5. And he went, really? And I said, yes, really. That's where the energy for power delivery is coming from to drive all the ICs on that board. Because that's where the energy gets delivered, is in the dielectric space between power and ground. And he said, but I've got signals between there. And I went, aha, shame on you. What I'm telling all of you is if you're using that nasty 6-layer board with power and ground on 2 and 5, regardless of the order, it's a bad plan. I'll tell you a little later how to fix that. There's an easy solution to solve that problem, and we'll talk about it a little bit later. One of the main goals of power distribution design is to maintain a low bus impedance, meaning to get our entire impedance of the power bus from the clock frequency, which by the way is the low end of the frequency spectrum, from the clock frequency out to a frequency referred to as 0.5 divided by rise time. Rise time in this case would be in nanoseconds. So if you had a device, a processor, a memory device, whatever, driving signals with a rise time of a half a nanosecond, 0.5 nanoseconds, the upper end frequency in this power bus would be 1 gigahertz. 0.5 divided by 0.5 is 1 gigahertz. If your rise times are 250 picoseconds, then the maximum frequency the power bus has to deliver is up to 2 gigahertz. And if you have rise times faster than that, gigabit level systems today have rise times often down in the tens of picoseconds. So the upper end frequency is 10, 12, 15, 20 gigahertz. Well, how are you going to get energy from a circuit board at those frequencies? You're not. And we'll talk in a second about how that's accomplished. So the target impedance basically should be the maximum noise voltage that you can tolerate in the power bus. And that should come from an analysis of your noise budget to good analysis. I won't get into that. Requires simulation, requires thought. Anyway, maximum noise voltage that you can tolerate divided by the maximum instantaneous IC current. Instantaneous meaning what? Meaning the current that's drawn, pardon me, to drive the transmission lines of the circuit board. If I have 50 lines that are being driven from an IC that's powered from 2.5 volts, and those 50 lines are driving into 60 ohm transmission lines, those 50 drivers, they'll be pulling 40 milliamps each. That'll be the current that each of those lines will pull. Instantaneous current. This is an important thing to keep in mind. All of the power, the high-speed power, the instantaneous high-frequency power that comes from a power bus comes during rise time of a signal. When a signal goes from a logical 0, to a logical 1, that's when all of the high-frequency current is pulled out of the power bus and pulled through the IC and launched into the transmission lines. So in that particular example, you would have, let's say, a target noise voltage of 100 millivolts, maximum 100 millivolts. And it's a long story why I picked that number. Those of you who attend the 3.5-hour class I'm doing at West, I will go into detail about why that's a good number and reasons to be thinking numbers in this range. Divided by the instantaneous current In this example, I said 50 outputs, 40 milliamps each, that's 2 amps of instantaneous high-speed current. Means that we need a power bus with an impedance of 50 milliohms, 0.05 ohms, 5/100ths of an ohm. Think about that. That's a very small impedance. And this isn't even a high current. What does power bus impedance have to be in a high-speed networking system where you're pulling maybe 100 amps and you still need to maintain no more than a few hundred millivolts of noise margin? We're talking about impedances down in the 0.001 ohm range in order to accommodate power delivery to devices of that type. This requires some serious design capability in the circuit board. For this example, though, we would simply need to get our impedance down below 0.05 ohms from the clock out to 0.5 divided by rise time. And as long as we can maintain that low impedance across that band of frequencies, we're golden. To do that, we're going to need capacitors, obviously, decoupling caps. In order to achieve this in any board that's pulling amps of current, you're probably going to need planes, meaning power plane and ground planes, and they should be put in the board as pairs, power and ground next to each other. The example I gave a few minutes ago of power on 2 and ground on 5 is a really bad idea. Now, when you're pulling really low end current and the board isn't all that fast, when you're using a microcontroller where your rise times are in the order of 2, 3, 4 nanoseconds, and you're only pulling maybe hundreds of milliamps or an amp or so of current, even at that rise time, yeah, then you probably can get away with that kind of thinking. But in anything that even vaguely resembles a high-speed board, it's a bad plan. You want power and ground planes together. And something else, the people who are operating in the gigabit domain, they're going to need to have OPD and ODC. What does that stand for? It stands for on-package decoupling and on-die capacitance. That means capacitance built into the interposer board, the substrate, inside the IC package, and maybe even capacitors put on the surface of the interposer, as well as ODC, which is on-die capacitance. Capacitance that's intentionally built into the die. Because when you get up into the 50 amps and above current range at the frequencies that some people are gigabit frequencies where people are operating today, you're not going to get the job done without having a lot of capacitance built into the package. And don't think these kinds of devices are cheap. I recently saw a microprocessor. Now, this was quantity 1. I imagine if you buy 1,000 at a time, you can get it a little cheaper than this. But I recently saw a microprocessor in quantity 1 that sold for $69,000. A microprocessor. Think about that. High-end microprocessor. Lots of ODP and ODC in that device. You can bet on it. It's designed for very high-end networking systems. Low impedance and low PDN impedance is achieved at low to medium frequencies with large amounts of capacitance. Requires different types and values of moderately high, medium low, and very low frequency capacitors. Everything from capacitors that are hundreds of microfarads down to the 0.1 and 0.01 microfarad types. You also have to have low impedance due to at high frequencies due to low inductance. The key to maintaining low impedance at high frequencies, other than the capacitance inside the package of the IC, the key to maintaining low impedance on the board at high frequencies is not high capacitance, it's low inductance. Low inductance is the secret to making the power bus a low impedance at frequencies above 200, 300, 400 megahertz, up to whatever frequencies you need to satisfy. This requires low inductance of IC packages. We're going to talk about how to do that. Power vias, decoupling capacitors, and planes on PC boards, or in some cases, plane segments. We're going to talk later about pouring copper on signal layers to enhance power delivery, and we'll discuss ways how that is done. And there's already been one question submitted regarding that, which we will answer at the end. Whether or not we can hit an acceptable impedance at high frequencies is dependent on both board inductance and IC package inductance and everything on the board. And vias are a major event when it comes to inductance. If your vias have high inductance, well, you're toast, pal. Speaking of vias, to keep inductance low, spacing between features matters more than feature size, and that includes vias. Somebody asked me recently, what's the inductance of that via? And I looked at him and I said, sorry, you can't answer that question. You can't tell me the inductance of a via. Oh, you can tell me the partial inductance, but so what? Who gives a rat's behind about partial inductance? I know PhDs do, but I'm sorry, I don't. What is inductance? Inductance is in a pair of vias. When you have a forward via and a return via. In the case of power delivery, a power via and a ground via. And the spacing between them has more to do with their inductance than their size. Let me give you an example. This pair of vias here, they're separated by 6 1/3 millimeters, which is 1/4 of an inch. They have 20 mil pad with a 10 mil drill, which is a 0.127 millimeter drill and a 0.05 millimeter pad, right? And or 0.02 millimeter pad, sorry. Sorry, I lied again, 0.5 millimeter pad. I'll get this right eventually. That pair of vias separated by 1/4 of an inch has an inductance halfway down through the board. I'm assuming that the power and ground planes in this board are in the middle, and we'll talk about other things besides that. There's better ways to do it. We'll talk about that in a little while. Assuming the planes are in the middle of the board, the vias go from the top of the board to the middle of the board. The inductance of that pair of vias is going to be about 1.2 to 1.25 nanohenries. Those of you who are going to attend PCB West, you'll be receiving a copy of the larger presentation, which has this slide in it. And I would encourage you to, in fact, those of you who are watching this now, take a screenshot of this and use this formula after we're done here and calculate the inductance of the vias if you doubled the diameter of those two vias, but yet kept them 1/4 inch apart. And what you'll find is that doubling the diameter, instead of making a 10 mil drill, a 20 mil drill in a 40 mil pad separated by 1/4 of an inch only decreases the inductance by about 15 or 16%. It goes down to a little over a nanohenry by doubling the via size. Taking this same size via and moving them close together drops the inductance to 1/2 a nanohenry. This is a 60% reduction by simply changing their positions. Inductance is ruled by spacing. Why? Because it has to do with the volume of the magnetic field. Remember, the energy's in the dielectric space. Where? Between the two vias. The further the vias are apart, the larger the magnetic field grows. Larger field means higher inductance. Push the vias together, the field shrinks and is condensed into a smaller, tighter space, and inductance goes down without changing their size, their length, or anything else. Goes down by 60%. Think about that. When mounting capacitors to a PC board, via location is a major driver toward inductance. If I have an 0603 capacitor, for example, as shown here, with a pair of vias at the end of the capacitor, going to the middle of the board, planes in the middle of the board again, with this capacitor will give us about a nanohenry of inductance, about 1,000 picohenries of inductance. If I take this same capacitor and put the vias on the side together, close together, the inductance of the vias drops to 1/2 a nanohenry, 500 picohenries. If I add a second pair of vias on the other side, it cuts in half again, down to 1/4 of a nanohenry. I know you don't always have room for 4 vias on each capacitor. I get that. But when you can, always put them on the side of the capacitor as shown here. At minimum, do this. And do this when you have the room to do it. That will minimize the inductance of the attachment of the capacitor to the planes of the board. And as you'll see in a little while, when you have a high layer count board with planes close together, all of the energy in the power bus is delivered to the IC through the planes. So you want to get the energy out of these capacitors and into those planes through the lowest inductance attachment you can, so that you minimize the energy losses in those vias. Think about that. Here is the inductance of, I'm just going to bring them all up, a bunch of different capacitors. An axial lead part through hole, nobody uses those anymore, at least not that I'm aware of, is very high, 2 nanohenries, 2,000 picohenries. A 1206 is a little more than half that, and that's a nominal inductance, by the way. Why nominal? Because the real inductance of a 1206 is not one number. The real inductance depends on the value and the voltage as well. Why? Because value and voltage are a function of the dielectric constant of the material in the stack of planes. There's a stack of planes inside of a capacitor. And those planes are, plus minus down through the stack up. Those planes have a dielectric between them that has a dielectric constant. It helps determine, along with spacing between the planes, what the value is going to be. The dielectric punch-through voltage of the dielectric determines the maximum voltage. So all of these things work together to determine how far apart the planes are going to be in the capacitor, what the dielectric constant of the material will be, and yada, yada, yada. And all of that affects inductance. A typical 1206 is going to be somewhere between 1,000 to 1,500 picohenries. Nominal value about 1250. 0805 nominal value about 1050. 1210, which is a larger version of a 1206, is going to be down under 1,000 picohenries, and so on as you go down through the list. Notice the 0201 capacitor has an inductance, a measured inductance of about 450 picohenries. A 1206 capacitor with the leads on the side have the same inductance. A side lead 1206, called an 0612, has roughly the same inductance as an 0201. If and only if you mount it correctly. And I'm going to talk about that in the next slide. The last thing here is a 16-pin ball grid array capacitor. I think it was AVX that originally generated this, and other people since have been making it also. It's a really low inductance part, as you can see, but that only happens when you mount it with 16 HDI micro vias, one in the middle of each pad, via and pad, 16 vias inside the part. You won't get that inductance otherwise. Be aware of that. If you route the leads out from the ball grid array cap and put a couple of vias outside the perimeter, forget it. You'll have the same inductance as the larger parts above there. So be aware of that. So let's look at these side lead caps. Let me just bring this up. If I mount the vias of a side lead cap as shown here, it actually drives the inductance of the attachment up. Versus if I put one pair of vias, one on either side, a positive, one to the top pin of the capacitor and one to the bottom, I will have lower inductance than if I put two vias as I've shown here. Why? How can that be possible? Because when you have two vias, you form two sets of magnetic fields. And these two magnetic fields, because they both have the positive side up, are the same polarity. Take two inexpensive magnets, toy magnets. They don't even have to be strong magnets. Put both north poles up and try to push them together. I defy you to push them together. Unless you're Charles Atlas, you're not going to be able to do it, because they're going to push back at you like nobody's business. Why? Because like fields repel each other. If you want the fields to attract, which will lower inductance, then you have to move the vias to this position. And that's the only way that you will get the inductance listed on the previous slide. Anytime you put vias put a pair of vias on the leads of a capacitor, like shown in this top figure, you actually increase inductance. Now, I've known people who do that with medium frequency caps, the ones that are, 10, 20, 50 microfarad caps. Based on the frequency they're pushing, who cares? I mean, the highest frequency that a 30, 40 microfarad capacitor can deliver is probably in the few hundred kilohertz region. I mean, it can't even deliver a megahertz successfully. So as long as you're not delivering high frequency energy from it, who cares? It's not a big deal. People sometimes do this with medium frequency caps to increase the current capability of the pair of vias. But if you care about inductance, you have to have opposite polarity vias near each other. That's what lowers inductance. Here's a study done by Dr. Bruce Archambault, who used to work for IBM. He's now retired. And I think he still consults with him, but he's no longer a full-time employee. And Dr. James Druniak from Missouri University of Science and Technology. They worked on this study together, and they looked at placing capacitors around a BGA. Now, they didn't put them under the BGA for a reason, which I'll get to in a little while. They placed the capacitors around the BGA, and they had 4 different configurations. They had them densely packed and all facing the same direction. So in the upper left arrangement, all the positive pins were up or to the right. In the next arrangement, they were still densely packed, but alternating, power ground, and so on. In the lower left was a spread apart non-alternating, and lower right spread apart alternating. In all 4 cases, they put the vias at the ends of the capacitors. Couldn't they have lowered the inductance in the bottom ones by putting them at the side? Yes. They didn't want to do that. They wanted to have 2 variables only. If they had put the vias at the side of the bottom 2 sides of the caps at the bottom 2 configuration, that would have lowered the inductance further in the bottom ones and wouldn't have given them real numbers about what they were actually looking for. They wanted to have 2 variables only and see the difference. Which of these 4 do you think is going to have the highest inductance? And I know, hopefully, you're all saying the upper left, because they're all facing the same direction. They're doing exactly what we talked about here. Don't do the upper one, do the lower one. And that's what the upper left is doing here. Here's a picture of the inductance of the 4 of them. The dark line is the upper left configuration. Keep in mind what I said a minute ago. If you spread out the capacitors, and there's really good reasons for doing that as well, not just to lower inductance. There's good reason to spread out the capacitors because it helps give a better spreading inductance of the fields coming from the caps into the part, and helps lower the spreading inductance also, which is a good thing. But on top of that, with these lower configurations, you could put the vias at the sides and lower inductance even further. So please keep that in mind. Let's talk for a moment about low-end microcontrollers and routing power. Very often with microcontrollers, which typically come in PLCC or J-leaded parts, where they have 4 sides with pins around the four sides of the part. And there are power and ground pins, usually 1 or 2 on each of the 4 sides. And in this configuration, because their rise and fall times are typically in the 2 to 4 nanosecond range, the maximum frequency that they're going to have to deliver, even with 2 nanoseconds, is only about 250 megahertz. And with a slower device than that, if you get a 4 nanosecond device, the maximum frequency, 0.5 divided by rise time, is only going to be about 125 megahertz, which is not that high of a frequency. Capacitors by themselves can deliver those frequencies without any help from planes. You don't need planes in a board of this type. That's why I'm talking about routing power in this configuration. How should you mount the capacitor in this case? The best way to do it is to put it relatively near the pins. Keep good manufacturability rules in mind. Keep good manufacturability rules in mind as you're doing this. Don't get the cap so close that people are not able to, what the heck is this thing? Please move this window away from what? I don't know. Anyway, don't get these so close that it's going to screw up the ability to solder either of these parts or desolder them for repairs. Remember manufacturability rules. As long as you do that, you can get them as close as good manufacturing allows, and it will likely be close enough. Why did we put the vias at the outer edge of the capacitor? Didn't you say, Rick, that raises inductance? Yes, that's what we want in this case. The capacitor is doing all of the heavy lifting, all of it. So you want to deliver the energy from the capacitor. Remember, all of the energy is going to come out of this capacitor only during the rising edge of the signal. Once the signal goes high, during the time it's high, during the time it's going low, and during the time it stays low before it goes high again, you've got all of that time to recharge this capacitor. So you don't need to recharge it through a low impedance path. You just need for its attachment to the IC to be a low inductance, low impedance path. And that's what mounting it in this way does. By putting the vias out to the edge, we actually increase the inductance of the attachment to the power rail, which serves to decouple the power rail from the IC and the IC from the power rail. We're raising the inductance intentionally to decouple the two. This is where the word decoupling came from. Back in the 1970s with TTL and other low-speed logic, we intentionally mounted capacitors like this. So the inductance of the capacitor attachment would be high because we knew there was plenty of time to recharge the capacitor, but there wasn't a lot of time for it to deliver its energy to the IC. So think about that. Now, notice the underlined statement here. Put the capacitor on the same side of the board as the IC. Why? Inductance of vias. If you put the capacitor on the other side of the board, you're going to drastically increase the inductance of the attachment. And I'm going to show you a plot in a minute of what would happen just to move that to the other side of the board. It's ridiculous how bad it gets. Never, when you're routing power or making direct attachment of capacitors to a part of this type. Now, with the BGA, you don't have a choice. But when you're making attachment to a part like this, always put the capacitor on the same side of the board as the IC, all of them, and make short, sweet attachments. What if you have widely spaced planes? Like what? Like a four-layer board. Four-layer boards don't have to be widely spaced, do they? Yes, they do. If you're buying boards that are 62 mils thick, 1.6 millimeters thick, because that's the thickness you buy, if that's what you're buying, and you ask for a four-layer board, the vendor is going to put about a millimeter of space between layer 2 and 3. So if you're putting planes on layer 2 and 3, they will be widely spaced. And there is nothing you can do about it except to pay extra to get them close together. Because if you ask for them to be close together, you will pay extra for it. Nothing comes in life for free that you have to, when you have to move a fabricator out of their normal domain, it doesn't come for free. So a 4-layer board, a 6-layer board with power and ground on 2 and 5, those are very widely spaced planes. Actually, any board, pardon me, that has the planes separated by 11 or more mils apart, separation, which is about 1/4 of a millimeter, is considered wide spacing of planes. In that particular configuration, the planes, even though they're widely separated, are still a capacitor, and they do store some energy. And so you want the via attachment from the IC to the planes to be a low inductance attachment. So you want the vias to be right next to the IC pins, either here or here. It doesn't matter. Either one is fine. Put the two vias next to each other. Remember, opposite polarity vias together, near the pins of the IC, and then mount the capacitor on the other side of the vias. Why? because the capacitor will still have a very low inductance attachment. Remember, it's doing most of the heavy lifting here. The planes are going to help, but they're only going to help a tiny, tiny bit because they're so widely separated. Their capacitance is almost nothing, and I'll show you that in just a moment. So doing this does give us some capability from the planes, which is helpful. Place the capacitor, again, on the same side of the board. Never put it on the other side of the board. That'll drastically increase the inductance of the delivery path, and that is what you don't want to do. If the capacitor is on the opposite side, yes, much higher inductance. The capacitor feeds its power to the IC before the planes. Why? Because the inductance of the capacitor and its attachment is lower than the inductance of widely spaced planes. Energy always comes from the lowest impedance path first. And in this case, that's the capacitor. But the planes will help a little. Here's what a single 0.1 microfarad 0603 package capacitor looks like. This is what its impedance curve looks like. This is a logarithmic scale. Note that it is. Both the impedance side and the frequency side are logarithmic. This is what a typical 0.1 microfarad cap looks like at the pins of the IC, measured at the pins of the IC in that configuration. One cap looks like this. If you've got a microcontroller that has a dozen outputs, each pulling 30, 40, 50 milliamps of current from a 2.5 to 3.3 volt or even a 5 volt output, this is probably going to be adequate to deliver power, especially because you're going to have probably 4 sets of power and ground pins around the part, maybe even more. And if you put a capacitor at each one of them, you'll get something that looks like this. If you need to lower the impedance, you could put 2 capacitors in parallel at that location, or you could put 3 capacitors in parallel. How about just making a larger value capacitor, Rick? You could do that, but that won't lower the inductance. If you make a larger value capacitor, all that will happen is the capacitive side of this curve will lower, but the inductance side will be the same as the top curve. So if you triple the value of it and still have 1 capacitor, you haven't really helped what you want to help, and that's the high frequency response curve. If you need to improve the high frequency response, you need to put more than 1 cap in parallel. What do the planes of a 4-layer board look like relative to these 2? Oh, by the way, these caps very often with a microcontroller, without planes at all, without a power plane, can do the work very handily. And I've seen it happen many, many times. What do the planes of a 4-layer board look like compared to this? They look like that. Jesus, really? That's it? That's all you got? With a 4-layer board, that's all you got. The impedance of those planes is higher at all frequencies than a single 1.1 microfarad cap. 1 cap is a better deliverer of energy than the planes of a 4-layer board. Are they going to help? Yeah, they'll help a little. And the beauty is they'll help a little at high frequencies. But boy, the help they're going to offer ain't much. These planes are basically almost useless. What if I put the capacitor under the part, or instead of mounting it to the IC like this, what if I put the capacitor, attach it directly to the planes? What would this one top blue line look like? It would look like this. If we put it under the IC and go through vias to get to it, or attach it to the planes, it'll look like this green curve, not the blue one. Can you imagine, can you see how much frequency fidelity we're losing by mounting it incorrectly? This is massive. Don't do that. Make sure you mount the parts the way they should be. And by the way, the impedance at the low end is easy to take care of. the voltage regulator module, the medium frequency caps, and a dozen other things will lower the impedance at the low end of the frequency curve. It's the high frequencies that we need to be careful of. And that's where low inductance makes a difference. And I'm going to show you in a little while how much of a difference good planes in a circuit board can make. We'll talk about that in a short while. What about closely spaced planes? As in what? As in 10 mils apart or less. Actually, I think closely spaced would be 6 mils apart or less. I like really closely spaced planes. Higher layer count boards, 8, 10, 12, 14 layer boards, things of that type. With closely spaced planes, the inductance of the planes is much lower, and I'm going to show you some inductance numbers of planes in a short while. The inductance of the planes is much lower than the connection inductance of the capacitors to the planes. As a result, during the entire rise time of the IC's output transition, remember, all energy gets delivered during rise time. During the entire rise time of the output transition, all decoupling energy, all of it, 100%, is delivered through the inner plane capacitance of the board. Meaning the capacitors, because they're a higher impedance, and I'm assuming a BGA here with higher layer count, that sort of thing, the mounting of the capacitors will be a higher inductance than the inductance of the planes. And as a result, regardless of how well we mount those capacitors to the plane, the low impedance, low inductance of the planes will dominate performance, meaning the energy of the capacitors will get dumped into the planes, and the energy will be delivered through the planes to the IC. As a result, you're going to love this, the location of decoupling caps is not important. They do not have to be close to the IC power and ground pins. And they sure as heck don't have to be under the BGA like ticks on a dog. They just need to be attached. They need to be close enough. Okay, Rick, close enough, meaning what? Meaning within the circle defined by rise time. Think about this. Energy moves in a circuit board in FR4 at about half the speed of light, about 6 inches per nanosecond. If I have a 250 picosecond IC, rise time of 250 picoseconds, a fairly high-speed processor, not super high speed, but a typical processor, the kind that many of us use. In 250 picoseconds, I'm going to reach out into that board 3/4 of an inch. And that's as far as that IC pin is going to be able to reach to pull energy in. So as long as you put your capacitors within this circle, they are close enough. Now, the reality is there's multiple power and ground pins, which means there are multiple circles. And the bottom line is, remember we talked earlier, distribute the capacitors away from each other if you can, get them out away from the IC within these circles. I was in Denmark 2 years ago doing a presentation, and somebody, there was a bunch of European engineers, obviously, and one of the people in attendance said, Rick, if you could put the capacitor close to the IC, wouldn't you do that? Wouldn't there be benefit in doing that? And I said, that's a really good question. And honestly, I haven't done enough with this to verify that closer versus farther. I mean, we've tested this theory, and what I just told you is absolutely true, but I haven't tested both those mechanisms. The moment I said that, there was a guy sitting in the crowd from Sweden who works for a company who makes very high-speed networking systems. And I mean, boards with 10, 12, 15 gigabit lines on them, really high-speed stuff. He said, Rick, we do this, and we have experimented with that. And we have found that if we put the capacitors out near the edge of this group of circles, we get better power delivery than if we crowd them in around the IC. And I said, why? And he said, we don't know why. We haven't been able to figure that out. He said our suspicion is that when you put them in close to the IC, you're breaking up the planes more near the IC, which increases the inductance of the planes at the point where you don't want the inductance to be high. And I think he might be right. I think that may be the reason. I don't know for sure. I'm just telling you, their tests have shown that putting the capacitors anywhere in this circle are all you need to do. And at really high speeds, you're better off to put them out near the perimeter. Let's talk about inductance of planes for a moment. Here's a set of planes. Look at this left three sets of curves. A red, a green, and a blue curve. Planes 14 mils apart. 14 mils apart. The red curve has an overall inductance. By the way, inductance is a per square measurement. Let me go back to the previous slide. The inductance of this group of circles will be constant regardless of their size. These circles could be 2 inches on a side or could be 4 inches on a side. And as long as they're an even constant shape, they will have a constant inductance. And that spacing, the inductance will be based solely on spacing. Spacing between the planes, not the size of the circles, will determine the inductance of the planes. So a slower part, one that has a 500 picosecond rise time, would develop circles twice this large, but they would still all overlap each other. And so their inductance would be the same if we had the planes separated by 14 mils as the smaller circles. You understand what I'm saying, I hope. It's like resistance. It's a per square measurement. So if you have a circle, whether it's a 1 inch diameter circle or a 10 inch diameter circle, if the planes are separated by 14 mils, they will have exactly the same inductance. The red curve is well above about 450 picohenries. The blue curve is about 250, and the green curve, and the blue curve is down around 50 or 60 picohenries. Why is there such a difference between them? Notice the color code at the right. The red curve indicates an IC that's mounted in the corner of the board. What happens if I mount this IC in the corner of the board? Well, the edge of the board cuts off the top of the circles and the circles on the left. And so I create an irregular shape, not a regular shape. So my per square inductance measurement goes up because I've lost plane area. I've cut off the plane area, and it drastically raises the inductance. If I put it at the top edge of the board, I'm only cutting off the top of the circles, but I'm still cutting away some of my power delivery area. Large ICs, high-speed power delivery, pulling amps of current, put them in the middle of the board. I could tell you stories for days about this. I could fill an entire day with stories about how bad it can get when you don't. Put them in the middle of the board. You can see how much lower the inductance is. Inductance of planes 4 mils apart is much lower when the thing is in the middle of the board than when they're at the edge or the corner of the board. Keep that in mind. What if you have planes that are up near the surface of the board? This is a drawing, but it's a drawing to scale of a board that I worked on when I worked for L3 Avionics Systems. It's a 12-layer board, and what you see is the exact stack up that we used. We had signals on the top of the board. We had a ground plane on layer 2. Very close to it, about 2 to 3 mils away, was a power plane on layer 3. There was a signal on 4, a ground on 5, signals on 6 and 7, ground on 8, signals on 9, ground and power and ground on 10 and 11, and signals on 12. With planes near the surface of the board, if you put the planes that are driving that BGA up near the BGA, in other words, the planes on 2 and 3, what I'm saying is, are the planes that are going to drive that BGA. In that scenario, should I put the capacitors here, or should I put them under the BGA, which is what people typically do? The answer to that question is not a matter of how far they are from the pins. It's a matter of loop area size of the inductance generated by the vias and the planes. You can see the planes are close together, 2-3 mils apart. So their inductance is going to be really low. If you mount the capacitors at the top or under the BGA, then this green area that you see will be the loop area that will form an inductance for those vias. And that loop area, even though it's short, is fairly large, because the loop area for the capacitors on top of the board looks something like this. And even though it's a much longer distance, that loop area is much smaller than that loop area. And the end result is that mounting the caps on the top of the board gives far superior power delivery in this case than mounting them under the BGA. Far superior. How much better? Here's 16 caps mounted under the BGA with a set of planes on layers 2 and 3 separated by 50 microns, which is 2 mils. The red represents the planes, the blue, the 16 capacitors. If I take those 16 caps and mount them on top of the board, attaching to those planes, their inductance, their impedance improves to this blue line. You look at that and you say, well, that's not that much of an improvement. Oh, this is a logarithmic scale, my friends. This is a 40% lowering in impedance of the attachment of those capacitors to the IC. It's 40% lower impedance than it was before. Think about that. Just by moving them to the top of the board instead of under the IC. Sometimes when the planes are near the surface of the board, you're far better off. Now, in reality, if the planes were in, in the center of the board, they were in the dead center of the board, layers, whatever it would be, 6 and 7, then it wouldn't matter where you put them really. You probably, in that case, would be better off to put the parts, the capacitors, under the BGA. But I'm going to tell you something. You put the capacitors under the BGA, and that plane curve that you see there will suffer badly. It won't be anywhere close to that good. I mean, it'll be nowhere close to that good of an impedance curve if you drop it down to the middle of the board, because this set of planes is plotted using both the capacitance of the planes, the inductance of the planes, and the inductance of the vias to attach it to the IC. And you drop it to the middle of the board and its frequency response is going to fall away. And the planes are not going to be that helpful. You need for these planes to help you out and to help lower the impedance at high frequencies. And the only way they're going to do that is to put them, in this case, with a high-speed part near the surface of the board. Here's a good example of a well-designed IC. This is a very well-designed IC. We'll be done with this presentation in just a short while, and we'll take questions. Here's a very well-designed IC. Why? Remember, what did I say about inductance? Inductance is based on proximity. See the dark green pads? That's ground. The other dark colors, red, dark blue, dark brown, purple, those are all voltage rails. All of the light colors are pins that are driving signals. All of the signals, every signal on this IC is 1 pin's distance away from power or ground or both, which means the inductance of the signal pins will be low. All of the power pins are next to ground, all of them, which will lower the inductance of the power pins. This is what future ICs are going to have to look like as speeds increase. Because if they don't expect things to work, for what it's worth. Let's talk about a couple of board stacks and then we will be done and we'll take questions. This is a 4-layer board that I talked about earlier, and I said it's an abysmal stack up. What's wrong with it? Well, the power and ground planes have basically no capacitance, and their inductance is ridiculously high because the spacing between them is about 1 millimeter. On top of that, what if you have to change layers with these signals? Where's the energy for the signal on layer 1 It's in the dielectric space between 1 and 2. If I move that signal through a via to layer 4, how am I going to get the fields in the dielectric between 1 and 2 down to the dielectric between 3 and 4? Well, the capacitors, the decoupling caps will help a little. But remember, decoupling caps only work up to 200-300 megahertz, and then after that, they're kaput. And what if you have a rise time fast enough that you have signals well beyond that frequency? You know what's going to happen? The fields are going to capacitively couple between those planes. But because they're so far apart, they're going to have to spread way out to do so. And in doing so, they're going to couple into all of the other vias in that area, which is going to create common mode current in every line that's anywhere close to the signal line that's changing layers. And that is probably going to lead to EMI. We had a major EMI problem with this exact board stack when I was just before I left Goodrich Aerospace in 1995. And we solved the problem by going to a different 4-layer board. We moved the signals to layers 2 and 3, made them strip line instead of microstrip, so we helped contain the fields of the signals. We put ground on the top and bottom of the board. We poured ground around with poured copper around all the ICs and the components. And when you do this, you've got to make doggone sure that all of your signals are right below or above a ground pour. You can't route a signal underneath the pads of the IC or underneath a capacitor because you won't have any ground there to reference it. Your signals must have a constant, steady ground reference. If they don't, you'll get field spread that probably will lead to EMI problems. So you have to be very careful where you put them. When we did this, we then poured power in around all the signals, and we kept moving signals around until we got all of this copper pour on layers 2 and 3 to make all of the attachments of power. We then attached all of the power plane segments that were on 2 and on 3. We attached them to each other every place where they overlapped with lots of vias. And every place where the ground pours overlapped, we attached the ground pours on the top to the ground pours on the bottom with lots of vias. How many vias? A via every 10th wavelength of the frequency of energy in the dielectric. Meaning what? What if your fastest rise time is 250 picoseconds? I'm sorry, let's say 500 picoseconds. That means your maximum frequency is a gigahertz. What is the wavelength in decay of a gigahertz? It's 6 inches. A quarter of that is 1.5 inches. That means you only have to have, a tenth of that. A tenth of 6 inches is 600 mils. That means you only have to have vias every 600 mils. Can you put them closer? Yes. Yes, you could. You don't have to, but you could. Anytime I do copper pours, if I can't attach a piece of copper to at least 2 vias, I blow it away. If it's so small that I can't get at least 2 vias in it, it's not worth keeping. Think about that. Every copper pour must be attached to something. Don't have loose random copper. Doing this versus the board on the left, we got a 14 or 15 dB improvement in the EMI signature. This is a board that had to be low layer count because of cost. And this solved our problem in an enormous way. Here's the planes I showed you earlier, but 4-layer board. When we redesigned this board to that, the planes looked like this. The poured planes, they're not even full planes. They're just copper pour. And because they're much closer together here than on the right than on the left, even though they're only partial pours, because they're close to ground, the impedance of the thing is much lower. The inductance of this is 5 times lower than the inductance of the planes of a 4-layer board. The capacitance is not quite 5 times lower, it's 4 times lower. But the inductance is 5x lower. It's 1/5 the inductance of the 4-layer planes. This is partly why it helped. There's a lot of reasons why that board stack helped. Here's the last couple more slides and we're done. 6-layer board, I talked about this earlier. Power and ground on 2 and 5. People tell me, oh yeah, if you swap power and ground, that'll solve it. Bull. There's nothing that will solve this problem. What's wrong with it? There's power and ground being pulled from the dielectric between 2 and 5. There's also signal fields in that same space. They are going to corrupt each other. As they corrupt each other, it's going to create a problem. You don't want that to happen. So, what can you do about it? One improvement that I've seen, pour ground on the top signal layer, pour ground on the second signal layer on 3, power on 4, power on 6, and now, instead of getting power from the dielectric on 2 and 5, where's power coming from? It's coming from part of the dielectric between 1 and 2. It's coming from part of the dielectric between 2 and 3. It's coming from part of the dielectric between 3 and 4, 4 and 5, and 5 and 6. And the end result is that instead of having large power fields that couple into signal fields, they're now next to each other instead of overlaying each other. So the signal fields are now isolated from the power fields, and the impedance of the power bus goes down by a lot. How much? By that much. My God, that's a 10x improvement. Yes, that's an order of magnitude lower inductance than the board on the left. An order of magnitude lower inductance just by adding the copper pores to the board. Remember, if you can't put at least a couple vias on a copper port, get rid of it. This is an 8-layer board recommended in one of the app notes that we used when I was at L3. It was for a 1300 pin microprocessor. And they said, we know some people need low layer count boards. This is the lowest layer count board we could get. We could pin out 1300 pins with. We had to have at least 4 signal layers to do that. What's wrong with this stack up? Oh, I don't know. Everything? Where does power 1, where is it going to couple to? What's the lowest impedance path for power 1? To the plane in power 2. It's not going to couple most of its energy to the ground plane. It's going to couple to power 2. 75% of the fields from power 1 are going to be coupling to the plane in power 2 and be in that dielectric between power 1 and 2. What's that going to do? It's going to create interference between power delivery of the two powers. The same thing, power 2 is going to couple most of its fields to power 1. Somebody said to me once, this is an 8-layer board, make the center core thick. Yes, you can do that. But if you make the center core thick, then power 1 is coupling all of its fields to the ground plane on 2. Guess what? There's a signal layer in between. You like EMI? I hope so, because you're going to get it. I can tell you with clarity, the company that did this, and they are a huge IC company. I won't mention their name. They said they got this to work in a lab, and I can believe with enough on-package and on-die capacitance in the IC, which I know it had because we used it, I can believe they got it to work. But I'll tell you one thing with crystal clarity. They did not pass EMI testing. Every time I do a public presentation, I call them out by name. And I say, anybody here from blah, 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 usually 4 or 5 hands go up. And I say to them, go back to your company, find out who created this board stack and who did the testing. Prove I'm wrong. Prove that they passed EMI testing, and I'll shut up forever. They've never called me back in 5 years. And I don't think they're ever going to, because this board wouldn't pass EMI testing. Here's a board stack up that was used in a 34-layer, very high density, very high speed board. Signal lines operating at 15 gigabits. Power to drive the 15 gigabit lines is on layer 1, ground on 2, same power on 3, ground on 4. Where does power come from here? It comes from 3 dielectrics. Do you know what the impedance of those 3 dielectrics is going to be with power ground, power ground? You have 3 dielectrics delivering the same power. The impedance of that is going to drop through the floor, which is what you want. And power delivery to drive the 15 gigabit lines is going to be smooth and clean as a whistle. This board was originally a 48-layer board, through-hole board. They made it an HDI board, and by doing so, improved the routing layers because they got all of the power delivery with HDI vias in the top and bottom of the board, and were able to route many more signals on each of the signal layers they reduced the layer count from 48 to 34 by going to HDI, which actually lowered the cost of the board and improved the performance. This is how you do it with very high speed, high layer count boards. Any questions? Let's take them.